All right, welcome to your lesson on function operations and this thing called composition. Okay, nothing in here is too terribly difficult. Maybe a little bit tricky with some domain, but that's about it. Okay, so we've got three objectives. First one, adding, subtracting, multiplying, and dividing functions. And it's pretty simple. We've done things like that before with polynomials. With functions, it works practically the same way. Okay, number two, we're going to find the composition of two or more functions. I think it's just going to be two functions. And then find its domain. That's the part that might be a little bit tricky, is to find in that domain. And then finally, this thing called the difference quotient. Find a difference quotient for a given function. Okay, so starting us off with objective one here, being able to add, subtract, multiply, and divide functions. And so in the diagram, in the image, you have, I guess this is like Chinese or Japanese or something. You got all these vending machines, and each one of the vending machines represents a function. And the reason why it does is because you stick in your coins, you push a button, and only one thing comes out. Whenever I select that orange thing right there, that orange drink, I want only that orange drink to come out, not the green one, right? So being able to add these vending machines together, subtract, multiply, divide, all of these functions. Okay, so reviewing the definition of a function, it is a relation. What a relation does is takes inputs and outputs, just pairs them up. It's a special kind of relation in which each input has exactly one output. So it takes members of the domain, which is a set of all inputs, and pairs them up with one and only one member from the range. Okay? Functions are thought of as being dependent relationships because what comes out of a function depends on what you stuck in. Okay? So whenever you go to add, subtract, and multiply these things, it's going to be just like doing it with polynomials. So whenever you add or subtract functions, you just add or subtract like terms. That's all it is, collecting like terms. Whenever you go to multiply functions, it's basically an application of the distributive property. I have to multiply these things together. Sometimes it's FOIL, sometimes it's one little thing times a couple of different things, distributive property. And then whenever you're dividing functions, you just write them as a fraction, as a quotient, and then you simplify what you can, if you can. Okay? So now let's just look at some examples right here, just straight from your book there. So the top one being an addition, and notice right here our two examples are functions. F of x is 5x and g of x is just x plus 2. So if I'm going to find a new function, which is the sum of those two functions, it's just collecting like terms. So you have a 5x plus the x plus 2, gather up your x's together, you got 6x plus 2. Very simple. Okay. Subtracting the two functions, I do exactly the same thing with the addition, but make sure you distribute the negative sign through here. So you'd be subtracting that x, you get 4x, and subtracting the 2, minus 2. Whenever you multiply, this is where the distributive property comes in. Just multiply the 5x times x to get 5x squared, and then times 2 to get 10x. And then finally, if I'm dividing my two functions, just divide them, just write them as a quotient and then simplify if you can. This one doesn't simplify, so I'd leave it like that. But on that one, I have this additional restriction. We've seen these functions before, that the x cannot be equal to 0 on the bottom. Well, actually, x can be equal to 0. The denominator can't be 0, so x can't be negative 2. So keep that in mind right here when we talk about the domain. The domain of your new function h, this is whenever I add my functions together, subtract and multiply and divide it, should be the set of all x values that are in the domain of both functions, both original functions. So here I have a Venn diagram. The part of the Venn diagram, so I have on the left-hand side what's in red, there's the domain of the f function, f of x, and then the blue one is the domain of the second function, the g of x. The part that's common to both of them, of course, is the slightly purpley part that's right there in the middle in the overlap. So there is the domain of the new function h. All right, Now, I have this additional restriction whenever it comes to division, which we saw in the last one. We have to make sure that that bottom function is not 0. So it's everywhere in that purpley part except for whatever makes g of x equal to 0. Okay, so this is just a general case, and sometimes that general case might be a little bit different. Maybe the domain of g, the second function, is entirely within the other one. In other words, maybe, for example, the red part of this is all real numbers, and the blue part of this is just x is greater than or equal to 0, while the part that you only get to keep for the new function is x is greater than or equal to 0. Okay? And then finally, here's another case. What if they're both the same? Maybe they're both all real numbers. Well, then that's the easiest case. That's where your new function is just all real numbers too, or whatever the original domains were. Okay, so let's just do a couple of examples here. Let f of x equal, and then I have a couple of power functions, 5 times x to the 3/2, and g of x is a negative 11 times x to the 3/2. And then do these operations and state what the domain is going to be. So f plus g of x is going to be equal to, just collect our like terms. I got 5 x to the 3/2, and then plus a negative 11 x to the 3/2. Since these variables they're essentially like terms, I can just add those up, which is 6x to the 3/2. Actually, that's negative. And so that's what, I'll call that h. That's what I should call that. Right? H of x. So there's this one. Now we have to figure out what the domain is going to be. So let's figure out the domain of both of the original ones. And this little half thing that's on the bottom of that exponent essentially means square root. It's an even root, and we know that whatever is underneath that thing cannot be negative. So for this, that just simply means that the domain here is x is greater than or equal to 0. And since the g of x function has the same root on it, that 1/2 power, its domain is also x is greater than or equal to 0. So in terms of like a Venn diagram, these things are both the same circle. They're the same domain. So the domain of this one must also be x is greater than or equal to 0. The end. Okay. Number 2. Well, look at this. This is tricky. G plus f of x. Does it matter which order I add them in? I'm going to have this time a negative 11x to the 3/2 plus 5x to the 3/2. I'm going to get exactly the same thing that I had before. And there's a name for that when it doesn't, like the order of the things do not matter. I'll have you think about that. We'll come back to it. I'll have you think about that for a second. Okay, here's the second part of this. Let's do some subtraction of these functions. So it's still exactly the same functions, and remember the domain here was x is greater than or equal to 0 on both of them. Okay, so whenever I go to subtract f minus g, subtract in that order of x, I got 5x to the 3/2 minus a negative 11, which makes plus 11x to the 3/2, and I get h of x, my new function, is 16x to the 3/2. And since they have the exact same domain for each part, this must also have the same domain, x is greater than or equal to 0. Okay, so like on the previous one, look, I just switched the order on number 2. So does it matter if I switch the order on subtraction? So this time I have negative 11x to the 3/2 minus 5x to the 3/2. This time whenever I subtract them, I get negative 16x to the 3/2 for h of x. And I can see that these two things, these two answers, they differ by a negative sign. One positive and one's negative. And that's what you should expect. Like whenever you subtract numbers, 3 minus 2 is 1, but 2 minus 3 is negative 1. Whenever I switch the order, they just differ by a sign. Okay, anyway, so again, the domain x is greater than or equal to 0. And it's finished. All right, so we did some adding, we did some subtracting. I think we need to do some multiplying and dividing. So let's multiply right here. We got two new functions. F of x equals 8x. G of x equals 2x to the 5 6 power. All right, let's multiply right here. That of x is equal to 8x times 2x to the 5 6 power. So you can multiply out the coefficients together. I get 16. X is the same base, so we want to add the exponents together. So that 1 is the same thing as 6 over 6, which is 11 sixths. So here's our function for h of x, and you can leave it like that. Domain issue. Well, for this one, it's linear, so that domain is all real numbers. And for this one, it's an even root. It's an even root again, so its domain is x is greater than or equal to 0. So I need, like, here is the all real numbers part, and then for g of x, this is x is greater than or equal to 0. That part's inside of the all real numbers. I have to take that smaller part, the more restrictive part. So x is greater than or equal to 0. There's its domain. Okay, g times f of x. I'm sure this is totally going to make a difference if I just switch the order, right? So this time I've got 2x to the 5 6 times 8x, and it's exactly the same, right? It's the same. So it has that same property that addition has. When the order doesn't matter, it's called the, it starts with the C. We'll see in just a second. Yeah, we'll see in a minute. Okay, so then finally we need to do some division, and that's what we're doing right here. So same functions as the previous one, where we said this domain is all real numbers, domain, all real numbers, and this domain is x is greater than or equal to 0. All right, so divide them in this order. When I divide them, I have 8x on top, and then 2x to the 5 6 on the bottom. So I can divide the numbers out, so that's just 8 divided by 2 is 4. They have the same base, so I subtract the exponents this time since it's subtraction, so that's 6 over 6, x to the 1 6. There's h of x. Okay, now I would go, just like on the previous one, I have to take this part for the domain, but if I look back before I simplified, down here, x cannot be equal to 0. Before I simplified, x can't be equal to 0. So that means I'm going to have to take it off of the domain too. So our domain this time is x is greater than 0. I don't have the equal to on it. Okay, g divided by x. So I'm going to switch the order this time. I have this time g on top, so 2x to the 5 6 divided by 8x. Again, divide the numbery parts, which is 1/4. This time I have x to the 6 over 6. Negative 1/6 power. Okay, which is basically 1 over 4x to the 1/6. Either one of these would be okay. Look at that, me just drawing that line straight through. Should I erase it? Should I? Okay. Now, whenever I say the domain, just like before, that bottom can't be equal to 0. Oops, that one too can't be equal to 0. So I say x is greater than 0. Right. So like I said, that kind of stuff, that's all pretty straightforward. If there's anything that's kind of sticky, it might be a domain issue. So that word that I was looking for is commutative property. Commutative property means that it doesn't matter what order that they go in, first and second and first. And that works for both addition and multiplication. But it doesn't work for division and subtraction, right? Well, it's just like with numbers. I wonder if the other properties hold as well. Anyway, so one last exercise on this video. It's a little application, but it's a pretty easy application. A small company sells computer printers over the internet. The company's total monthly revenues R and costs C are modeled by these two functions. So R of X is 120X, and C of X is 2,500 plus 75X, where X is the number of printers that they sell. So the first question here is, what is R minus C? So number one, R minus C of X is equal to, my R is 120X minus, and I'm going to subtract both parts of this, so 2,500, and then I have to also subtract the other part, so 75X. Think of it as having parentheses that I distribute the negative sign to. Okay, so I have, let's see, 120 minus 75, borrow 1, and that's 5, and that's 45. So I've got 45X minus 2,500. The final question, the second part of the question here is, what does this thing represent? If I take off my revenue, revenue is how much money the company makes, and I take away from it all the costs that the company had to put into making their product, what is left over? What's left over is profit. And so that's what that function would give you if you subtracted those two. Okay, so that's it for this first objective. And let's look forward to the next one where we do some compositions.